Today we are diving into a machine that totally changed physics. It took a brute force problem and solved it with this, just beautiful, elegant spiral. This is the story of the cyclotron.
So think about it. It's the biggest question in particle physics, right? How do you actually study something that's way too small to see? You can't just, pop a proton under a microscope. So to figure out what our universe is made of, you have to get a little creative.
And the answer they came up with? Well, it's pretty wild. You basically accelerate these tiny particles to almost the speed of light, and then you smash them together. The pieces that fly off tell you what they're made of. But getting them up to that speed, that was the real trick.
Yeah, the first attempts, these things called electrostatic accelerators, were kind of clunky. The idea was simple. You give a particle one giant push with an electric field. But if you wanted more energy, you needed a bigger push, which meant cranking up the voltage. And you can only go so high before the electricity just arcs through the air. It's called electrostatic breakdown. They were basically hitting a brick wall.
And this is where the story gets so cool. Instead of building a longer and longer runway, a completely new idea came along. A way to get all that power, but in a space that was just tiny in comparison. So how on earth did they do it?
So let's break this down. The old way of doing things, the linear approach, had pretty much maxed out. Physics needed a smarter way to get things moving. Okay, so here's the big conceptual leap. The old model was basically a one-and-done deal. One big push, and that's it. The new idea, the cyclotron, was to use a circle. Instead of one massive shove, what if you could give the particle a whole series of smaller, perfectly timed kicks? By making it go in a loop, it could cross the same accelerating gap over and over and over again, gaining more energy with every single pass.
And the person behind this genius idea was Ernest O. Lawrence. His invention was so groundbreaking, so transformative, that he won a Nobel Prize for it in less than 10 years. It completely changed the game for experimental physics.
So how does this thing actually work? How do you get a particle to spiral outwards, going faster and faster with every single loop? Well, it all comes down to a really clever dance between two fundamental forces.
First up, you've got the push. This is the engine. Picture two hollow D-shaped metal chambers. They actually call them Ds. In the gap between them, you apply an electric field that flips back and forth really fast. Every time a particle zips across that gap, bam, the field gives it a perfectly timed kick that makes it go faster.
But a push by itself would just send the particle flying off in a straight line. That's where the second force comes in, the guide. A huge magnet creates this constant magnetic field. Now this field doesn't add any speed at all. Its only job is to change the particle's direction, bending its path into a nice, smooth arc.
Okay, and this is where the magic happens. You start a particle right in the center. It gets pushed across the gap, it picks up speed. Then, the magnetic field bends its path into a perfect semicircle. But now, since it's going faster, that semicircle is a little bit wider. It arrives back at the gap just as the electric field is flipped, ready to give it another push. More speed, a wider arc. Another push, a wider arc. You see? It spirals outwards, gaining incredible energy, until it's finally shot out at the edge.
For a while, this system seemed absolutely perfect. I mean, the synchronization was beautiful. You want higher energies? Just build bigger magnets. But as they kept pushing the limits, they slammed into a problem. And this wasn't an engineering problem. It was a problem with the fundamental laws of physics.
And when you're dealing with these insane velocities, the normal, everyday physics that made the cyclotron work so perfectly, well, it starts to break down. Because now you're playing in Albert Einstein's sandbox. And the universe has rules.
So here's the issue. Einstein's special relativity says that as a particle gets closer and closer to the speed of light, its effective mass actually increases. It gets heavier. And a heavier particle is harder for the magnetic field to bend, so it starts taking longer to complete each loop. And just like that, the perfect timing is gone. The particle shows up to the gap late for its next push, it falls out of sync, and the acceleration just stops.
But, physicists are a pretty clever bunch. They didn't just scrap the whole design, they adapted it. They came up with two major upgrades to get around Einstein's cosmic speed bump.
So two solutions emerged. The first one was the synchrocyclotron. It basically said, okay, if the particle is slowing down its rotation, let's just slow down the electric pushes to match it. And it works, but you have to do it in pulses. The second, and much more advanced solution, is the isochronous cyclotron. This one keeps the electric pushes constant, but it changes the magnetic field, making it stronger towards the outer edges. That stronger field gives the heavier particle an extra little tug to force it to keep up the pace and stay perfectly in sync.
This design gives you a continuous, really powerful beam, and it's what most modern cyclotrons are based on.
So you might hear about the giant colliders like the LHC getting all the headlines, but Lawrence's invention from almost a century ago, it is far from a museum piece. In fact, it's become this absolutely essential tool, especially in a field you might not expect, medicine.
Just get a load of that number. Around 1,500. That's how many cyclotrons were being used in hospitals and research centers around the world back in 2020. And a big reason why is that their compact power is just perfect for having them right on site where you need them.
And this is why it matters so much to all of us. A lot of these cyclotrons are busy creating medical isotopes. Those are the radioactive tracers that are critical for things like PET scans, which help doctors find cancer and heart disease. Others are used for particle therapy, where they fire a super-focused beam of protons directly at a tumor, destroying it with pinpoint accuracy while leaving the healthy tissue around it almost untouched. And, of course, they are still vital tools for basic science, helping us understand the very nature of matter itself.
You know, from a device that could fit on a tabletop and push the absolute boundaries of physics to a medical workhorse that saves lives every single day, the journey of the cyclotron is just a stunning story of brilliant design. It really makes you wonder, as we keep refining this elegant spiral of power, what new challenges will it help us solve next?